This diagram outlines the system architecture of our FPGA-based arcade game Strike-A-Light. Let's examine the key components and their interactions. The binary to BCD converter processes player scores, outputting separate digits for tens and ones places for both the players. The system employs a 1 Hz timer for game countdown functionality. A 2-bit counter operating at 100 Hz coordinates the multiplex display refresh cycle. This ensures smooth visual output. The core game logic maintains score counters for both players and manages the state machine that controls gameplay flow. It interfaces with the VGA controller to render the display using color coding to differentiate the players. The decoder translates counter signals to activate the appropriate 7-segment display digits. This works in conjunction with the BCD converter to present clear real-time score updates. This integrated system architecture demonstrates how digital logic components work in concert to engage and create a responsive gaming experience. Each module performs its specialized function while maintaining a seamless interoperability with others. Let's examine the control logic behind Strike-A-Light through its finite state machine implementation. From idle, the system activates on start button press, transitioning through init for hardware initialization. The show light state triggers random button illumination, while wait input handles player response detection. Valid inputs trigger score update before cycling back, creating the core gameplay loop. The 60 seconds timeout provides a clean transition to the end state. The complete cycle concludes with return to idle upon subsequent start button press, demonstrating the machine's re-entrant design. This FSM architecture provides robust control flow while maintaining clarity in game state management and transition logic.
A 5.5 power source is connected to the normally open terminal of the push button switch. This switch also connects to one of the PMOD ports on the FPGA board. Meanwhile, the FPGA is also connected to a relay module through a different PMOD port, with the connection going to the input control pin of the relay. Both the FPGA and the relay module share a common ground to ensure proper signal reference. The relay module requires a 5.5 volt power supply to operate, which is provided externally. On the relay module, the output terminals include the normally closed, normally open, and common pins. The LED of the push button is connected to the normally open terminal of the relay. When the push button is pressed, the FPGA detects the input and sends a high signal to the relay's input pin. This triggers the relay to switch its output from the normally closed pin to the normally open pin. As a result, the common pin connects to the normally open terminal, completing the circuit and allowing current to flow through the LED, which causes it to light up.
The major challenges we faced were as follows. Our first technical challenge was the circuit debugging. During development, we faced persistent circuit debugging issues. The integration of multiple subsystems from button inputs to VGA output required meticulous signal tracing and validation at each integration point. Our second challenge was high voltage integration. A critical hurdle was interfacing industrial 220 volt buttons with our 3.3 volt FPGA. After extensive research, we implemented relay based isolation circuits, solving the voltage mismatch while maintaining safety and reliability. Our third technical challenge was the input debouncing. Debouncing errors initially corrupted our scoring system. We resolved this by implementing 50 millisecond hysteresis check in our Verilog code, ensuring clean signal registration for accurate scorekeeping. Our fourth technical challenge was the input registration. We discovered our push buttons weren't registering input consistently. The solution came through proper implementation of pull down resistors, stabilizing the input signals and eliminating floating voltage issues. Strike a Light isn't just a game, it's a demonstration of real time digital control, hardware software integration, and the creative potential of logic design. From signal debouncing to VGA output, every element reflects the core principles we've learned throughout the semester. This project challenged us, taught us, and above all, brought our knowledge to life, one strike at a time.